Okay, let's dive right into this explainer and completely transform these Cambridge IGCSE Mathematics past papers into a highly structured, absolutely bulletproof mastery workshop. Welcome to the ultimate strategy session for the Cambridge 0580 syllabus. Today, we are tackling a massive challenge that literally trips up thousands of students every single year. Let me introduce you to two very typical students taking this exact exam. First up, we have Alex. Now, when Alex sits down for a paper, he completely overloads his answers with raw mathematics facts. He writes down every single formula he can possibly remember on the side of the page, but there is zero analysis, there is absolutely no logical flow to his working out. Then, on the other end of the spectrum, we have Sam. Sam is constantly watching the clock, completely stressed. He rushes through the paper, completely missing the specific command word requirements of the questions, and makes these really silly, avoidable algebraic errors that cost him easy marks. You can practically see the red pen marks multiplying on their papers right now. But today, we are going completely away from those flawed approaches. We are going to build solid, highly structured arguments with stress-tested evidence. I am going to give you the exact blueprint to turn those red marks into green check marks. By organizing the source material into these 5 distinct mathematical themes, we can actually spot the hidden patterns that govern the entire exam. We're looking at core algebra, formulas and geometry, advanced equations, indices and sequences, and finally, proportions. And as we go through this, we're going to apply what we call the mathematics success blueprint. This is all about command word decoding and applying a structure similar to the Peel framework used in essays, point, evidence, explanation, link, but perfectly adopted for mathematics. So, your point is stating the correct formula. Your evidence is plugging in your specific numbers. Your explanation is your step-by-step working. And your link is tying that final calculated answer directly back to what the question actually asked. All right, let's jump right into Section 1, Core Algebraic Foundations. We absolutely have to start here, specifically looking at how we expand and factorize, because this is the bedrock of everything else on the paper. Looking at this problem pulled straight from Student Assessment 2, I want you to ask yourself what the very first logical step is. But wait, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the problem. The command phrase here is absolutely crucial: factorize fully. It is not just asking you to find one simple common factor and call it a day. It wants this expression broken down into its absolute simplest possible form. Now, when our student Sam sees PQ minus 3RQ plus PR minus 3R squared, he completely freezes up. There are 4 terms here. There is no single letter or number that perfectly goes into all 4 of them. Alex, on the other hand, might try to randomly divide things out or write out totally unnecessary exponent rules, completely losing the thread of the question. I want you to be the strategist here. The key insight is recognizing that a 4-term expression without a universal common factor usually requires a brilliant little technique called factorizing by grouping. And this step-by-step breakdown brilliantly illustrates how grouping terms reveals a hidden common bracket, seamlessly turning a messy 4-term polynomial into a simple, clean product. Notice exactly how this breaks down. First, we literally just split the expression right down the middle. We look only at the first 2 terms, PQ minus 3RQ. What do they share? They share a Q. So we pull that Q out to the front, leaving us with P minus 3R inside the brackets. Then we look at the second pair of terms, PR minus 3R squared. They clearly share an R. We pull that R, and miraculously look what happens. We are left with the exact same bracket, P minus 3R. Now I promise you, this isn't a coincidence. It is completely by design. Because that entire bracket is now a common factor for both halves of the equation, we can extract the whole bracket itself. We are left with our common bracket, P minus 3R, multiplied by the leftover pieces, which are Q plus R. We have successfully taken a complex, intimidating problem and structured it into a clean, stress-tested algebraic proof. Full marks. Now, what's really fascinating about this next slide is how incredibly intimidating fractions look to most students until you actually applied basic cancellation rules. This is exactly where students like Sam throw away easy, guaranteed marks. The command word here is simplify. When Alex sees fractions containing variables like x, his immediate instinct is to panic and waste 5 minutes trying to find a common denominator. But wait, stop and actually look at the operator. We are multiplying here, not adding. You absolutely do not need a common denominator to multiply fractions. This is a classic, deliberate trap set by the Cambridge examiners just to see if you are actually reading the command word and checking the math operators. The rule for multiplying fractions is simple. Top times top, bottom times bottom. So x times 3 gives you 3x on the top. 7 times x gives you 7x on the bottom. So the crucial point here, your link back to the question, is that the variables simply cancel each other out, leaving us with a totally clean, simplified fraction. Once you have 3x over 7x, the x on the top and the x on the bottom essentially divide each other to become 1. Poof, they're gone. You were just left with 3 over 7. It really is that simple. Please don't let the sudden presence of letters make you forget the fundamental rules of arithmetic you mastered years ago. Trust the process. Moving right along to Section 2, Real-World Formulas and Geometry. Let's transition from those abstract letters floating on a page and start applying our math to actual physical spaces and shapes. This specific formula, pulled from Assessment 3, is the ultimate blueprint for solving cylinder geometry problems. Volume equals pi r squared h. But here's the thing. The actual Cambridge exam will very rarely just ask you to move forward. They love to ask you to work backwards. Sure, if they just hand you the radius and the height, you simply plug them in, multiply by pi, and boom, you have your volume. But honestly, that's a low-level, one-mark question. What happens when they give you a giant cylinder with a known height of 75 centimeters, a known volume of 6,000 cubic centimeters, and then they ask you to find the missing radius? This is exactly where the examiners separate the average students from the top-tier mathematical strategists. You absolutely cannot just guess and check your way out of this. You need to manipulate the formula. You need to confidently shift the variables around the equal sign without breaking any fundamental mathematical laws. So instead of just blindly plugging in numbers and hoping for the best, how do we manipulate the algebraic foundation we just learned to completely isolate the radius? The command phrase here is make r the subject. What does that actually mean? It means our final answer needs to look like an equation that literally starts with r equals and then has absolutely everything else on the other side of the equal sign. Right now, r is trapped. It is being squared, and it is being heavily guarded, multiplied by both pi and h. I want you to think of this like carefully unboxing a really delicate present. You have to meticulously remove the outer layers one by one before you can finally get to the core inside. We need to systematically reverse the mathematical operations that are currently happening to r. By simply reversing the operations systematically, we've successfully and safely rearranged the entire formula to solve for the radius. Notice the beautiful step-by-step clarity of our working here. This is your explanation in the Peel framework. First, because our r squared is currently being multiplied by both pi and h, we have to do the exact opposite. We divide both sides of the equation by pi times h. This safely removes them from the right side and leaves us with v over pi h equals r squared. Okay, we're close. Now r is almost completely alone, but it still has that pesky squared exponent attached to it. What is the mathematical opposite of squaring a number? It's taking the square root. So we take the square root of the entire left side of the equation. R equals the square root of v over pi h. If Alex and Sam applied this highly structured sequence instead of panicking, their papers would instantly jump from a failing grade to full marks for this question. It's all about methodically showing your evidence. Now, applying this exact same logic to a pentagon problem from Assessment 5, we can set up a massive equation where the sum of these 5 complex angles equals exactly 540 degrees. This right here is a brilliant test of linking physical geometry back to core algebra. The examiners don't just give you the actual degree numbers for the angles, that would be too easy. Instead, they give you these algebraic expressions in terms of x, but they do give you the golden key, the universal law that the sum of the interior angles of any pentagon is always 540 degrees. So your logical first step, your point, is to literally write out all those expressions added together. 9x plus 5x plus 10 plus 6x plus 5 plus 8x minus 25 plus 10x minus 20 equals 540. From there, you simply combine all your like terms, isolate your x just like we practiced, and solve. This is exactly how you build a flawless mathematical narrative on the page. All right, take a breath. We are now ready for Section 3, Solving Advanced Equations. Before we dive into finding these complex unknowns using simultaneous and quadratic formats, stop scrolling, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's dive straight into this specific high-stakes problem from Assessment 4. I want you to look at this like a data scan challenge. What is the core trend jumping out at you right now? Look closely at the Q variable. The coefficient for q is exactly the same in both lines of the equation. It's a -3. This is incredibly important information. When a rush student like Sam sees this, he might randomly try to substitute terms or just guess numerical values, completely wasting time. But the examiner has deliberately lined up those two -3s to specifically test if you know the elimination strategy. The absolute biggest mistake students make here is trying to add the two equations together. Think about it. If you add -3q to another -3q, you get -6q. You haven't eliminated anything at all. You just made an even bigger mathematical mess. This step-by-step breakdown right here shows exactly how identifying those matching coefficients allows us to eliminate a variable entirely. Because the mathematical signs on the 3q are completely identical, they are both negative, we must subtract the entire second equation from the first one. Let's walk through it. 5p minus -2p, that gives us a positive 7p. Now for the magic, -3q minus -3q gives us 0. It completely vanishes. Then, -1 minus -8 gives us a positive 7. So our messy problem becomes just 7p equals 7. Suddenly, an impossible-looking system simplifies instantly to p equals 1. But we aren't done. The final logical step is to take that newly found p equals 1 and substitute it right back into the first equation to find q. 5 times 1 is 5, so 5 minus 3q equals -1. Shift that 5 over, and -3q equals -6, which means q equals 2. Absolute perfection. Now moving on to quadratics, the absolutely critical takeaway here is to always rearrange your equation into the standard form of ax squared plus bx plus c equals 0 before you even think about applying your formula blueprint. This is an absolute non-negotiable rule of mathematics. The command phrase here is explicitly telling you to use the quadratic formula. But look closely at the equation provided. 2x squared minus 7 equals 3x. It is completely out of order. Our student Alex would immediately just start plugging numbers in, a equals 2, b equals -7, and c equals 3 into the formula. And you know what? He would fail the question instantly. You must subtract that 3x from both sides first to get 2x squared minus 3x minus 7 equals 0. Only then can you correctly identify your a, b, and c values to safely plug into -b plus or minus the square root of b squared minus 4ac all over 2a. Quality control comes first, execution comes second, always. Fantastic! Let's transition now to Section 4, Indices and Sequences. This is where we shift our brains from solving rigid equations to discovering flowing patterns hidden within numbers. Looking at this beautiful set of data extracted directly from Assessment 9, we can clearly see that the common difference dictates the multiplier for our n term. Let's do a quick visual scan of sequence A. The numbers go 1, 5, 9, 13. Ask yourself, what is the jump between each number? It is going up by exactly positive 4 every single time. That difference of 4 is your anchor. It immediately tells you that your algebraic formula must start with 4n. But wait, if you plug in position 1 for n, 4 times 1 is 4. But our sequence actually starts at the number 1, not 4. So how do we logically get from 4 down to 1? We subtract 3. Therefore, the unbreakable rule for the sequence is 4n minus 3. Let's verify this strategy with sequence B. It goes 1, -2, -5, -8. The jump this time is going down by -3, so our multiplier is -3n. To make the very first term equal a positive 1, we must add 4. The rule is exactly -3n plus 4. This is a stress-tested system that literally never fails if you follow the steps. Now, moving from linear sequences to exponential sequences, ask yourself how the physical gap between the third and sixth terms actually helps us find the ratio. This is a fantastic, higher-level Cambridge question. We aren't just adding or subtracting the same number anymore. We are multiplying by a common ratio, which we call r, to get from one term to the very next. Think about the physical jumps. To get from the third term to the fourth term, you multiply by r once. To get to the fifth term, you multiply by r twice. To finally land on the sixth term, you have multiplied by r a total of 3 times. So mathematically, the sixth term is equal to the third term multiplied by r cubed. Now we just set up our equation with the evidence. -1 equals 27 times r cubed. Divide both sides by 27 to get -1 over 27 equals r cubed. Finally, to isolate r, you take the cube root of both sides. The common ratio r is -1/3. Boom, problem solved. Excellent work so far. For our final major topic, Section 5, the power of proportions. we are going to tackle a concept that heavily relies on establishing a constant, comparing direct versus inverse relationships. This text brilliantly illustrates the absolutely critical distinction we pulled from Assessment 11. Identifying whether a relationship is direct or inverse literally dictates the entire architectural blueprint of your equation. Direct proportion is very straightforward. As x goes up, y goes up. The formula is simply y equals k times x, where k is our magical constant of proportionality. Think of it like an hourly wage. The more hours you work, the more money you make. It goes up together. But inverse proportion, that's a seesaw. As x goes up, y goes down. The formula fundamentally changes to y equals k divided by x. Think of travel time. The faster your driving speed increases, the less time it actually takes to arrive at your destination. You must completely memorize these two distinct blueprints, because if you confuse them on the exam, every single subsequent calculation you do will be completely wrong. So applying this, when you read the specific phrase, inversely proportional in a word problem, you immediately, without hesitation, write down y equals k over x on your paper. That is your point. Looking at the data provided in this table, if we have a fully completed pair of numbers, like we know y is 4 when x is 8, we use that specific complete pair to unlock the entire rest of the puzzle. It's like finding the cipher to a code. We absolutely cannot solve for the final requested answer until we know exactly what our unique constant k is for this specific scenario. So the absolutely crucial point here is that k acts as your heavy anchor. Once you find it, you can solve any proportion question the examiner decides to throw at you. If the rule is y equals k over x, then by simply multiplying both sides by x, we discover that k is always equal to x times y. If we use our complete pair from the table, where x is 8 and y is 4, we just multiply them together. 8 times 4 gives us a constant k of 32. Now we rewrite our master equation for this specific problem, y equals 32 over x. This customized equation is now our ultimate tool. For the final step, the question asks, what is x when y is 20? We plug 20 in for the y variable, 20 equals 32 over x. Rearrange it algebraically to x equals 32 divided by 20. Simplify that down and you get exactly 1.6. That is a perfect, logical, stress-tested, full-mark answer. Look at what we've accomplished. By spotting the underlying patterns and applying these precise formulas step by step, you are literally building bulletproof, stress-tested mathematical proofs, not just guessing numbers. Let's quickly recap the complete mathematics answering system we've developed today to get your mark potential up to 100%. We have 3 golden rules that guarantee top marks. Rule number 1, command word decoding. Don't rush like Sam does. Know the exact difference between factorize, simplify, solve, and evaluate. Rule number 2, the Peel framework. Point to your formula, use evidence by plugging in numbers, explain with step-by-step working, and link to the final answer. Rule number 3, the time management matrix. Don't overload the page with irrelevant, messy facts like Alex does. Write precisely what is required to earn the specific marks allocated, and then confidently move on to the next question. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Subscribe right now to at Ace the Exams IGCSE and click that bell. Don't let another exam pass you by. So I ask you, which of these foundational mathematical tools are you going to actively practice first? You have the complete strategy now, but execution requires real discipline. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Pick your weakest area, apply these methods, and let's go turn those red marks into green check marks.